Welcome everyone to a video inspired by gasoline, or petrol, benzene, essence, call it what you will. The question I am answering today is how far a car moves on one molecule of gas. You would think this is pretty easy. Find out how far the car goes per liter, multiply that by how many molecules are in a liter, and boom, answer. Only, well, it's more complicated than that because just as there are many different names for gas, there are many different molecules in it. Here is a table of common hydrocarbon alkanes found in gasoline. The more carbons, the larger the variety of possible molecules with the same formula, which are called isomers. Both ethane and propane have one isomer, butane has two, and pentane three. It quickly becomes absurd, and when I searched for isomers, I didn't even bother to check if it counted all possible types. Whatever the sum is of that column, the real value could very well be much higher. We need to narrow it down, and while gasoline does not have an exact composition, one analysis finds pentanes, hexanes, heptanes, and octanes of all kinds account for more than 70% of all hydrocarbons in a sample of gasoline 95. Within that selection, we find perhaps the most famous of all hydrocarbon fuels, octane. Here are those 18 isomers, and among them is the standard bearer for octane, 2,2,4-trimethylpentane. Yup, the most famous octane is, by organic compound naming convention, not even an octane. But why is it the standard? If you drive a vehicle, you want it to run smoothly, and the fuel itself plays a bigger role than you may think. When researching fuels, 2,2,4-trimethylpentane, also known as isooctane, was used as a standard for fuel performance along with normal heptane. Under testing conditions, the N-heptane performance caused considerable engine knocking or uneven fuel combustion and was assigned a performance rating of 0. Meanwhile, isooctane performed significantly better and was assigned a rating of 100. These performance values are where the octane rating comes from. At the pump, you are met with many options of octane rating to choose from. If you pick the 91 octane here, you can expect the fuel performance to be equivalent to that of a mixture of 91% isooctane and 9% N-heptane. If we want to know how far a car goes on one molecule of gas, then we need some molecules to compare to. I think it's only fair to start with isooctane for two reasons. First, it's a standard when talking about gasoline, and second, its longest chain is only 5 carbons long, which should be by length among the smallest molecules present in gasoline in significant quantities. To find length, I'm using the wonderful website moleview.org. Since the measurement is from the center of hydrogen atoms on both ends, I'm going to round up to 0.7 nanometers as the length of this molecule. But how to choose another? Fittingly, it is the octanes themselves that are the biggest molecules found in double-digit percentages in fuel samples. N-octane, with all 8 carbons in a straight chain, will serve as the high end for the molecule size. Going back to MolView for the measurement, and rounding in a similar fashion, gives a molecule length of 1.07 nanometers. This gives us an average fuel molecule length in meters of 8.85 times 10 to the negative 10. The next piece of information needed is how many molecules are in 1 liter of these substances, and for that I need the densities. 1 liter of isooctane is 692 grams, and for N-octane it is 703 grams. Now how many molecules is that for each? Well, the molecular weights are identical, 114.2 grams. Dividing the masses by 114.2 results in a weird unit called moles, which represents a quantity. The use of moles brings us to the reason this video is posted on Mole Day, because every 1 mole is 6.02 times 10 to the 23rd somethings, which of course in this example are molecules. Since 1 mole is 6.02 times 10 to the 23rd molecules, we just multiply that by the number of moles and we get, unsurprisingly, massive numbers of molecules present. Using these two hydrocarbons as our standards, then the average number of molecules in a liter of fuel is 3.68 times 10 to the 24. We can put that number into the equation from earlier. As for the efficiency, a quick look at my car reveals it has been operating at 17,400 meters per liter. Now that the equation is filled in, we can finally get the answer to the question. My car moves a whopping 4.73 times 10 to the negative 21st meters, or 4.73 zeptometers per molecule burn. This is not even close to our assumed average fuel molecule length. In fact, the molecule length is so much bigger that my car needs to burn 187 billion molecules just to move the length of a single molecule. If you are curious about your own car, simply put its efficiency in meters per liter into the following equation. The output is the number of molecules yours needs to burn to move the length of 1 molecule. This works for gasoline, so if you have a diesel engine, use this equation instead. And while you probably won't thank me for leaving you with some homework, I will thank you very much for watching. When I started developing this video, I wasn't intending on making one fit for mole day, so hopefully you enjoyed how I shoehorned it in anyway.